You know, usually when we think about things moving, we just assume there's a motor or a push, right? Like some kind of physical energy behind it.
Right, yeah. I mean, our physical intuition really demands a force, like a car needs gas.
Exactly. But if you zoom way, way in, like down to the microscopic level inside our own cells, that intuition completely falls apart.
It really does, yeah.
Yeah.
Things just naturally spread out all on their own, like no engine, no pushing, nothing.
Which is wild. So today we are doing a deep dive into exactly that. We're breaking down a set of whiteboard notes comparing two fundamental biological processes, diffusion and osmosis.
Yeah, and we're going to strip away all the textbook jargon because we really want to help you understand exactly what these processes are and, well, why they actually matter.
So let's start by unpacking diffusion, and we want to keep this absolute beginner-friendly. According to the notes, diffusion is just the movement of solute molecules, so like the stuff dissolved in a liquid from an area of high concentration to an area of low concentration.
Right. And the key detail here is that this is passive transport.
Oh, meaning it takes absolutely zero energy.
Exactly, yeah. Zero energy required. The molecules just naturally move down what we call their concentration gradient.
Right, right. Until they hit eventual equilibrium, which the notes say is where everything is just evenly spaced out.
Yeah, they just bump around until they find that open space.
So is diffusion basically like, being at a packed party and people just naturally drifting out into the empty hallways to get some space without even thinking about it?
That is exactly what it is. I mean, nobody is actively pushing you out the door. It's just the sheer random bumping from the crowd that makes people spill over into those less crowded areas.
Okay, that makes total sense. So the salute, the partygoers, they just spill out into the open space.
Spot on.
But cells aren't just open rooms, right? They have barriers. So what happens if there is a semi-permeable cell membrane in the way?
Well, that thematic shift brings us right to osmosis.
Okay.
Because if the solute, those partygoers, are trapped and they physically cannot cross that barrier to find space, well, the universe still demands balance.
Right.
So the liquid itself has to move instead. And in biology, that liquid is almost always water.
Wait, water, but osmosis is the exact same principle as diffusion, right? Just for water.
Exactly. The notes actually show water moving through these special channels called aquaporins.
Aquaporins, okay, got it.
Yeah, and water diffuses from high water concentration to low water concentration.
Hold on, I'm a bit hung up there. How can water have a concentration? I mean, it's just water.
Well, think of it like this. If you have a highly concentrated saltwater solution inside a cell, there is literally less physical room for the water molecules.
Oh, because the salt is taking up all the space.
Yes, exactly. So the water concentration inside is actually lower than the pure water outside.
Wow, okay.
So to balance the scales, water just rushes in through those aquaporins.
Just moving straight in. But wait, if water keeps rushing in, the cell's volume is going to increase, right? Like it's going to swell up.
It does, and the notes warn that this swelling leads to turgor.
Turgor, right. Which I assume is fine for plants because they have rigid cell walls.
Yeah, it keeps them standing upright.
Hmm.
But animal cells, like ours, don't have that protective armor. Right. So if too much water rushes in through osmosis, it can actually lead to lysis.
Lysis. Wait, does that mean bursting?
It literally bursts open.
That is wild. A completely passive zero-energy process has enough raw power to just explode a cell.
I know. It really shows how unstoppable the drive toward equilibrium is.
Okay, so to keep it simple, the ultimate cheat sheet from the bottom of the notes is this. In diffusion, the solute moves. But in osmosis, the water moves.
Perfect summary. Both processes are just moving things from high to low concentration using absolutely zero energy.
It's just the raw mechanics of how things spread out naturally. But, before we wrap up, that brings up a really strange contradiction that I want to leave you with.
Oh, what is that?
Well, the notes state that diffusion leads to eventual equilibrium, right? Which means the net movement totally stops.
Right, everything is perfectly balanced.
But a living cell requires constant movement of nutrients and water just to survive.
Oh, I see where you're going with this.
Yeah, so if being alive requires that constant exchange, wouldn't reaching a state of perfect, unchanging equilibrium actually be fatal?
That is a profound thought. Being alive is basically the act of constantly fighting off perfect equilibrium.
Definitely something to ponder the next time you find yourself naturally drifting toward the empty hallway at a crowded party.